Hey guys, what's up? Eddie Yahoo here with KissAnalog.com. Today I have a pretty cool experiment, or well, I don't know if it's an experiment or more of a demonstration that I want to give you. And it has to do with the front end of a power supply. So I want to show you some signals, all right? Now, I did a rant on power cables. I've done a couple of them for audiophiles. Guys are spending say $50, that's cheap. $200, that's still on the cheaper side. They go thousands of dollars for these power cables, and they feel like they can hear the difference, okay? And I have tried to do these rants and explain that they don't, or they cannot. So I want to show you some signals and kind of show you how the power is processed through the power supply, or at least the front end today, okay? And I want to kind of show you what happens to that signal and how essentially ludicrous it is to think that these subtle differences you could make on a power cable could have anything to do with what ends up happening to your power as it goes through your power supply or your power amplifier, right? Your power amplifier has a power supply in front, right? And so the power supply provides power to your audio amplifier. And we're going to get to that section later. But today we're going to start off with the front end of the power supply. And we're even going to skip the EMI section, the part between the AC receptacle and the circuitry, the filtering that happens before the transformer. We're going to start at the transformer, okay? We're going to put power into the transformer, and I'm going to kind of show you that. Okay, so here's my setup here. Guys, still trying to organize things. I got a lot of cleanup, and I'm getting rid of equipment. I'm going to start eBay selling it, things like that. So, as a matter of fact, I'm going to change the scope I have up here to another scope. That's another discussion. But, yeah, so, all right, so here's the thing. The power supply, the front end of the audio amplifier, mini amplifiers, especially the high-end ones, they're still linear, what people refer to as linear power supplies. Really what a linear power supply is, I mean, that terminology is misused. That's not correct. When switchers come out, high frequency switchers, people start differentiating the new kind of power supplies that happened 20-some, 30 years ago as switching power supplies. And they said, oh, these are linear power supplies. Well, a linear power supply has to do with how it's regulated. And, the power supplies I have back here, they're linear power supplies. They're actually adjustable linear power supplies, right? They're bench supplies. So those things are linear, okay? The front end of a linear power supply before the regulation is not linear. It's a low frequency switcher. And that's what converts the AC to the DC. So that's a low frequency switcher, and I'm going to show you those waveforms, okay? So the ironic thing is some of these audiophile companies, they also sell these things that they call like regenerators or whatever. It's essentially a power supply that takes AC, converts it to DC, or at least some of it to DC. Some of these things are done in a weird way, but essentially they end up giving you AC clean, supposedly clean AC out, which, okay, that's for another rant. But anyway, so it's funny because, okay, the one guy I've talked about a couple times, Paul at PS Audio, they make these things, these regenerators or whatever they call them, AC regenerators. So he even says in a video like I just watched of his, how what's so great about them is they regulate the voltage. And so that's what I mean by the ironic side, is because the amplifiers, most of these audiophile amplifiers, they do not regulate the power supply rails because the thing would be just too big. The audio amplifier itself requires these big heat sinks. To regulate the power for the audio amplifiers, they require huge heat sinks too, maybe equally in size. So boxes would be gigantic. So it's funny because they've sold audiophiles the idea that unregulated supplies are better, and they're not. Even Paul talks about how the regulated supplies and how they're going to be moving to switchers, and switching power supplies are an art, and it's going to take them, a few years down the road before they can start converting over. I think they've already got one, but they're going to start pretty soon. They'll all be switchers, and they'll all be regulated. So, and then what will he do with this reconditioner thing? Because then that won't be required anymore, right? Most switching power supplies can operate typically down from 80-90 volts up to 265 volts. So they're universal, and they can be used here in the States and overseas without switching a button on the back from 120 to 220 or something like that. They just do it automatically, so they can regulate all those voltages. Doesn't matter. So those reconditioners that he sells, they won't be required anymore. I'm sure they'll come up with another reason why they are. Anyway, so what I want to do is talk about how the power is conditioned. So I've got this huge toroidal transformer, which, by the way, I think it's probably okay to say now, but I bought these surplus from a company who made them for Dynaco, if you guys know who Dynaco is. So pretty high end, and they had extras, so I bought them. And this is back when I lived in North Carolina. So I still got a bunch of them. I got a couple boxes, I think. So, well, they're all individually boxed because they're so heavy. So anyway, I'm going to use that to power some diodes here. This is my bridge rectifier in front. I'm going to show you a close-up of this, okay? But so then I have this big bank of bulk capacitors, right? So we first step it down, and then we go through the bridge rectifiers to make it pulsating DC, and then we come out with both a plus and a minus voltage rail for the audio amplifier. So this is, a board that I bought pre-made, and it's meant to power audio amplifiers. Here, let me show you a whiteboard. All right, let me just show you this so I can kind of try to get the glare off. I think it's off. All right, so here's our transformer, okay? And what I've got is line and neutral. It doesn't matter which one you put line and neutral in. But anyway, I put line neutral, and I put the dot up here on this side. So the dot shows kind of polarity. When this goes positive, then this dot goes positive, that dot goes positive. So these are essentially just stacked on top of each other, put in series. And then they're tapped off. The two windings, the two leads here on the windings come out to my return, okay? And then this one goes to the plus, and this one comes down to the minus. And so I got the diodes kind of drawn in a way that maybe it makes sense. But anyway, it's a bridge rectifier, right? So I've got my voltmeter here. I'm going to have some differential probes looking at the voltage coming in to the transformer. And then I'm going to go across one of the windings to show you what it looks like coming out, okay? Then it's going to go through this, and then I have, this is like 4 capacitors, and this is 4 capacitors, okay? So then I got my bulk, capacitors out here to give my power supply rails, my V plus, my V minus, in reference to this return. But I'm only going to take the V plus, V minus, and go into the active load. That way I can use one active load to power this whole thing. Okay, now what I did is I made some notes down here. This section here, the transformer, it provides your step down, right? So it's magnetic coupled, and as you build a magnetic field in this thing, then you're going to transfer, you're going to build a voltage over here, which then you can pull off current and you can supply power to the secondary side. Primary side, secondary side, okay? And we're going to step the voltage down. Typically you step down a lot of times, for audio amplifiers, right? And so it provides step down and isolation. That's really the two main functions. And also, I guess, 2 windings, so we can have a plus minus voltage. All right, so then we have a bridge rectifier, and that's our low frequency switcher. So these diodes commutate. What that means is they turn on and off as the voltage goes, because it's AC here, and then when this is plus, this diode turns on and it charges up that cap, and it comes all the way down here through the minus. So essentially you can just think of it this way, or you can think of it as this loop and think of it as this loop, you know. So, and then when it reverses and this is plus down here, then this guy is plus. He comes this way, and he finds his way back right up here to the plus. And then he comes down and he goes minus, and this time he takes this diode and comes up here. And so he completes that loop, okay? So there you go. There's your bridge rectifier. And the bridge rectifier is, you got these diodes turning on and off. And now the thing is when the voltage goes plus here, the current, this is positively, you know, you got a positive current flow waiting to flow. But when that capacitor over here is charged up to, you know, after the first so many cycles, it eventually gets charged up, right? When it's charged up, then the voltage here has to climb high enough to forward bias the diode to charge up the cap. So it's only going to charge it for this small sliver of time when the voltage, you know, this top of the sine wave gets high enough that the voltage is higher than what's on the cap, and the diode turns on. And then the same thing when it's, you know, high enough on this side. It has to be high enough to come up here and charge again, okay? So you end up with these pulsating currents, and they're switching on and off. It's a switching power supply. And it's good to think of it that way, because then you understand the current, the RMS current, it's not continually flowing. It's only flowing in pulses when the diodes turn on and off, okay? So you get these pulsing currents, and when you picture the voltage here, the sinusoidal voltage coming and coupling over here, and you get sinusoidal voltage on this side, the current's not sinusoidal, guys. It's pulsing. And so if you thought like a power cord and some conditioner or whatever here did a lot to make this, you know, the electricity so much cleaner, and so it sounded really good once it got to your amplifier, this thing's trashing it. It's jumping all over it. It's like somebody carrying this little umbrella in a rainstorm, and then you walk through this crowd of people that are jumping up and down in puddles and just splashing water everywhere. It's just, you might have kept dry out here, but then they're splashing this stuff and getting you all wet. As a matter of fact, that current waveform is transferred all the way out to the output of the power supply. So you need an EMI filter so your audio amplifier is not destroying the power, you know, making a lot of noise for all the other things that get plugged into the circuit. People are always worried about, you know, plugging in things into the same circuit that their audiophiles equipment is plugged into. But every piece of their audiophile equipment has these kind of power supplies that are just banging the heck out of the current. And so they have to protect themselves from one another. It's, yeah. So what happens here, this is where the magic happens. These big old bulk capacitors that we all love, you know, that we love to see them, right? Those big old bulk capacitors make all this AC, all this pulsing, all this craziness over here into DC voltage and DC current. Well, the current is actually dependent on what's happening over here, where this active load would be your audio amplifier, right? So if it's playing music, it's going to be pulling current through here. Now, the reason your amplifier is not going to create a lot of issues in the power supply on these caps is because what really causes problems, switching noise and EMI and all these things, because we haven't talked a lot about that. We talked about, oh, shielding and doing all these things to make it quieter. But really what happens is when these guys turn on for that narrow pulse and you get this big current, it almost looks square wave. Those fast rising edges are where the noise comes from. When current's traveling across traces or wires or whatever really fast, they're going from 0 to like, you know, 0 to 60 in 1 second. So when you're transferring that kind of energy or that current quickly, everything looks inductive, right? At high frequencies, things start looking inductive. At low frequencies, things look capacitive or resistive. At low frequencies, those wires look resistive. But at high frequency, they look inductive. And so when you're all of a sudden switching that current on this high pulse, then all the inductance, you got this transformer. Okay, you're going, yeah, but see, that's why the low inductive power cable helps. Guys, you got this huge inductive transformer here. This thing's Henry. I mean, it's like millihenries. It's huge. It's lots of millihenries. When you have 60 hertz low frequency, you want impedance here. You don't want a lot of current going through your transformer to try to run it, right? When you're not running power, you want this to be high impedance to your source. So it means it has to be lots of inductance, okay? So what that means is a little bit of inductance over here means nothing to this, okay? Where the inductance counts is between the transformer here, the output, and the capacitor. That's where the inductance means something, because this stuff is happening quick, big pulsating currents, okay? So this is really where it's more meaningful. But once you get into the capacitor, now you got nice even voltage and currents here. So we'll put current probe here so you can watch that. We'll put it here so you can see what happens on the other side of the transformer. And then we'll put one over here, okay? I've only got so many probes or inputs to the scope. I need an 8-channel scope to show you all this. But I think I'm going to use the Pico over here because it's 12-bit and I can show you, it's 14-bit actually. I can show you some really good definitions of what the signals look like here, okay? And over here, the 8-bit scopes are going to be fine because it's, you know, it'll show you the signal. We'll be able to show you what we want to show you. All right, so let's do it. Now, by the way, guys, just before I jump into it, remember when I talked about that magnetic field when nothing's happening? There is some current flow. There is a magnetic field that builds up here. And I've shown it in a video a few years ago where there's an inrush current, not because of these capacitors. I disconnected all this stuff and I showed the inrush current just in the transformer. So when you first turn it on, this transformer goes whoop, it kind of, you know, builds a field real quick. And then once it builds that field, the current slows down and everything starts coming, you know, so the inrush is over. All right. There are systems that maybe some of you guys have worked on where that's, you know, pulled breakers and caused some issues. I've worked on systems like that. So transformer inductance, big transformers can cause a big inrush, okay? And, you know, maybe at the end of the video, maybe I'll show you that again on this, but yeah, I don't know. We'll see if we have time. But I'll put a link down below where you can watch it on an earlier video. What I'm going to show you though is as I bring voltage up, and that's how we're going to start. We're going to start off bringing the voltage up at a low voltage and just come up so you can kind of see how things start to happen. At a real low voltage, these guys aren't turned on yet, and so you're going to just see a sine wave of current. It's like, where's that current going? Well, it's going through here. It's the reactance of the primary winding, and so it's just traveling here, but it's also building a field on the secondaries too, okay? So you're seeing a little bit of current there. It'll be a sinusoidal waveform. When I come over on this side, you won't see that sine wave anymore. It'll just be the little glitches of current charging up the caps. At a certain point, you'll start seeing the glitches on both sides when the diodes turn on. But I'll bring it up slow so you can kind of watch that because it's kind of interesting. So we're going to zoom in, look at small currents, and you're going to see. So, all right, so we're getting back to the power cord. Those small, subtle differences you think the power cord could be making that affect your sound quality, well, there's some even bigger stuff that's still subtle that's happening here, and that's what I'm going to show you. I'm going to show you these subtle things, and then I'm going to show you the things not so subtle. I'm going to show you those big splashes, and you'll see how ludicrous it is to think that your power cord's doing anything, okay? Because this is the noise generator right here. It's between your EMI filter and between your bulk capacitors. It's a big minefield that the power has to come through. So this is power processing, right? This is our first stage of power processing. First stage, well, we can even break this first. So really the first stage is the EMI filter, and then second stage is the transforming, stepping down to isolation, and then the third stage is the low frequency switcher, and the fourth stage is making DC. Because without the caps you have pulsating DC here. So then we make our DC. Alright? So there you go. Alright, let's take a look. Alright, so let's first go through the setup. Okay, so I'm going to use the mixed sig. I've got a differential probe here, and it's tied to right here, these two pins here. And this is the AC power coming out of my iTech AC power source. Okay, it's the IT7321, super nice. And so it's going to come over and connect up right here. And we're looking at the differential probe. So we're looking right at the power into the transformer. There's two windings in parallel. That's why there's two whites and two blacks. And this is the power cord tying them all together. And then I have two current probes you can see right now. And one reason why I'm going to leave one here, and I'm going to move the other one around to show you the difference, okay? So as we come back up here, one current probe is right here, and that's this guy, okay? CP503, super nice. And the other one is this guy over here. And it comes down this little board right here, which is the CP2100B. And that's a super nice one too. And you'll see, they both work great. So I'm trying to get all the wires out of the way. All right, so then what we have is another differential probe. And that's this guy here. Love this differential probe too. And it comes over here. And you can see it is the MDP 1500, okay? And it comes over here right now. We're tied to the input off of the transformer secondary. So the secondaries are right here, okay? Two of them, yellow and red. So we have a red one up here, and then the yellow one of that, you know, the other side of the winding is tied to the red one, top side of the next one, and they both go into the return post, okay? And then the yellow one at the bottom negative one. So we'll look at these two here, the closest ones to us. Okay, so we'll look at one of the windings. There's diodes on both sides of the heatsink, okay? And so I've got two of those here, so there's actually four of those devices. And then we have our positive voltage bank here and our negative voltage bank here. So you see the stripes over here, that's the negative side. Stripe of this one's tied to the positive one of this one. So that's here in the center. And coming over here, we can see that I have the load tied to the outside, plus and minus, okay? So then the load comes up here, and I started off the red and black, and then I had to couple them together, and then come up here to the iTech active load, okay? And it's the IT8512A. So just kind of keep you on all of them. And that display looks blinky in the thing. Sorry about that. But okay, so maybe I'll have to get the other camera so that when I'm showing you things. And then back to our mix sig. So yellow, 5 volts, that's our input voltage. And then the output voltage is the purple one. And then the input current and, well, both current probes are on the same spot right now. And they're both right here. I've got to change the multiplication of this one because that one is showing too high. It should be 10x. Okay, there we go. And then I'll drop it down here. Okay, so that's 10 milliamps. So I'll make them both 10 milliamps. Okay. All right, so now we're ready to bring it up. All right, guys, so what we're going to do is we're going to start off looking at this guy here. And we're going to bring up the voltage nice and slow. Okay, and I'm going to go ahead and turn on the output. Okay, and you can see a little bit of current's flowing. We got 1 volt. I'm going to bring it up a little bit. Okay, right about there, we're getting some current spikes. Now let's go look at the scope. Now we're seeing some current spikes, okay, on the scope.
All right, let's repeat that again. This time I want to show you the waveform so you can see the peaks charging the caps every time I make these small adjustments. Even small adjustments make huge peaks. Surge currents.
Okay, and you can see a little bit of currents flowing. We got 1 volt. I'm going to bring it up a little bit. Okay, right about there, we're getting some current spikes. Now let's go look at the scope. Now we're seeing some current spikes, okay, on the scope. So the yellow waveform, here, let me make that a little bit bigger. That is the voltage coming in, okay? That's the, I got 4.1 volts on the iTech AC power source. And then down here it says 4 volts, almost 407. So yeah, so just barely lost a little voltage, okay? Now, the purple one is the voltage off the secondary of the transformer, okay? So those are the 2 voltages. Now, the other small waveforms, the little blue and the little green one, here, I'll make the blue one bigger. Okay, now that's 4 milliamps per division, so it's pretty small, but hey, we're looking at subtle things. See the sine wave? That is what's going into the transformer, just to magnify the transformer, okay? So that blue one, the sine wave, that is just going to the transformer. That's just the magnetizing current, okay? If you looked at the X of L at this voltage, that would be the current that would go into it, okay? So it's about, 4.9 milliamps. But part of that is this big spike. So see these big spikes happening at the yellow waveform, at the peaks of the yellow waveform? That's our bridge rectifiers turning on. They're just starting to turn on. But look how sharp that peak is, even at only this level. So 4 milliamps per division, it's about plus minus 4 milliamps peak. But then this peak spike here is 1, 2, 3, 4, like 5. It's about 5 divisions, where the sine wave is about 1 division. So that's a pretty big spike. And see how it doesn't actually happen at the peak of the current waveform, happens at the peak of the voltage waveform, right? That's where the rectifiers turn on. And look how narrow it is. It's very narrow. We can spread it out a little bit so you can kind of see what that looks like. So now this is 2 milliseconds per division, so it's only on maybe about 1 millisecond. I mean 1.5 milliseconds at the base of the sine wave here, the blue sine wave. Now the green one, that's just not amplified, but it was 10 milliamps per division, so it looks just like the blue one. So these current probes are really nice. They track each other really well, but they are on different tables. So if I see, I can only make that 10 milliamps per division, and the blue one I can go a little bit higher. But if I go back to 10 milliamps, you'll see they lay right on top of each other, okay? All right, so if I take one of those and current probes and go to the other side of the transformer, let's just do that. Okay, now I'm on the secondary side of the transformer. So I just put this guy right here on the secondary winding, okay? And I still have this one up on the primary winding going in. So look over here. Now, the blue one, now that it's on the secondary side, here, let me make it bigger since I can do that. See how flat it is? It's flat and then it has a peak. It doesn't have that sinusoidal curve that the green one did, because we're on the secondary side of the transformer. That sinusoidal part is magnetizing current. It stays in the transformer. And as we go up in voltage, it's going to go up in current. It's just essentially a linear thing. It's X of L, okay? But you can see the how flat it is, and then there's this big peak, or there's this big spike, okay? Now, here, what we're going to do is I'm going to creep the voltage up a little bit while you watch these waveforms, okay? All right, so I'm going to creep it up. There's 5. Whoops. Now, the blue one's gone off screen, so I'm going to have to make it go a little smaller, okay? So now it's 10 milliamps per division, just like the green one. So now you can see how there's still, the peaks still pretty much lay on top of each other. And the green one has that sinusoidal waveform. Okay, now let's go 6 volts. Now, I mean, look, guys, we're only talking 6, 7 volts. But if you're thinking subtle differences from a power cord, You know, we're looking at subtle differences here, right? This is ground floor. This is what's actually happening in the power supply. And this is at the smallest of levels. This is only 7 volts in. This gets amplified, obviously. We go 10 times up, 70 volts. You can imagine these waveforms are going to grow huge. Whoops, lost one of my differential probes. Hold on a sec. Camera strap grabbed it. That is not good. It's a good thing these things are well insulated. I'm going to turn off the voltage just to be on the safe side. And you're going to see a little surge current this time. So that'd be kind of fun to watch. Now, we don't have any load. You know what? Actually, I'm going to turn on... Here, let's turn power back on. Okay? Here we go. Saw a little surge there, right? Had to charge up those caps again. And also the magnetic waveform and the transformer. Okay, now we're running back like we were, right? Okay. All right, guys. So that's pretty interesting, right? So we're at 7 volts. It's... like no power, because the only power that's going in is charging up the caps and whatever resistors and stuff like that. So there's almost no power. The AC power source doesn't even recognize any power at this point. So let's go ahead and add load. Now what we're going to do is jump up to here, okay? And I've got this guy set up, and we're going to turn on a load, all right? So here, let's go to constant current. And then I'll creep this up to 0.5 amp. Okay, we're going to turn it on. Okay, look at that. And we have 9 volts, 0.5 amp. Okay, there we go. All right, now we come back down to AC power source, and we can see we got about 5.9 watts. Okay, but here I want to show you something. Look at that blue waveform. Isn't that crazy? Here, let me adjust that blue. Let's bring it down a little bit. 20 milliamps per division. But before I do, we're going to see that big spike that's going off the screen, right? Let me get a few more waveforms so you can see this. But look at that blue waveform. Now, I'm going to turn off a couple of waveforms like the green one. Get it out of our way for a minute. And let me turn off the purple one too. Okay, we got the yellow, the input voltage coming in. And now look what the current is looking like, okay? Now this is the current that's going into the bridge rectifier, okay? It's on the secondary side of the transformer. But look at that. It's a square shelf. Then it shoots up in this peak, and then it drops down, a square shelf, and then it does it again. Isn't that kind of nuts? Now that's AC coupled. Let's DC couple this thing. There we go. Okay, so... that's a trick on your scope, okay? Because your scope, when it's AC coupled, it's got a capacitor. So it kind of, you know, so when you see those DC or those shelves kind of opposite levels, doesn't make sense. That's because your capacitor in your scope has to charge and discharge. So anyway, that's what it looks like. Now we're back to the flat thing again, but not quite flat. Here, let's go back to 10 milliamps per division. Look how it goes when it settles. First it overshoots and then comes back. Okay, all right, so let's bring this down so we can see the peaks. All right, we got 1 amp per division now, okay? So now there's what your waveform looks like going into your board, okay, on the secondary side of the transformer. Let's pull up the other one, okay, and let's drop it. Let's also AC or DC couple it, okay? And let's change the divisions. All right, 1 amp per division. Now look, they're almost the same. So the AC waveform part, it's in the milliamp range, and these peaks have just made them look so small in comparison that all you see these gigantic peaks. I mean, they're gigantic in comparison to the subtle things that are happening in the background, all caused by your power supply. Not what's coming into your power supply, but is being created by your low frequency switcher. Pretty interesting, right? Also, now, this AC power supply actually has a really clean waveform, but here, let's kind of go up in value. First, you know, let's look at the power factor just for fun. The power factor is 0.72 at 5.9 watts. Now I'm going up to the load and I'm cranking it up to 0.6. So, okay, there's 7.2 watts, right? But now let's go ahead and bring the voltage again. And let's watch the weight. Well, I gotta drop the yellow waveform down to 5 volts per division. Okay, now let's go ahead and bring it up. All right, so let's look at the purple waveform. Let's look at the voltage on the transformer, okay? Now look, there's your voltage on your transformer. Now, that's kind of interesting. Okay, so the voltage of the transformer, here, let's move the yellow. I'm going to turn off the yellow one for just a moment. Look at that one. It's kind of getting squared off. Do you see? As the current all of a sudden shoots up, it causes an impedance, a voltage drop in your transformer winding, so it squares it off. So, curious, right? Now, this is a huge transformer. We're only pulling, a couple watts at this point, so it's no big deal. It can handle this, but that's pretty interesting artifact, right? So let's go ahead and bring in the voltage some more. Okay, and now look at the purple waveform. It's starting to, I don't know, it's not quite square. Where the current first takes off, it kind of pulls it down, then it kind of straightens itself out a little bit, if you know what I mean. It's a little bit of a sinusoidal bump in there. All right, guys, so I've turned it off for a moment. I've just saved the screen. Now, what do you think of that? Now, so you can see a couple things happening. This transformer, it's a big, inductor, right? So it has so many millihenries, and now we could calculate that based on the numbers we saw, right? Because we know what voltage we put in. We could see that current that's flowing, that sinusoidal current. That's just going through the transformer. That's just to magnetize it. And that's the X of L that it sees on the primary side, okay? Now, there is some reflected inductance from the secondary side that's coming back across, that's loading it down, right? So there's all that stuff going on. And when the diodes kick on, those current spikes are gigantic in comparison to the sinusoidal current that's going on inside here, right? So you can see why I like to call these low frequency switchers, because it really talks about what's going on, and it really describes the action that's happening. When people say linear, there's nothing linear about what we just saw, right? So I just thought this would be a really good idea to show you the inner workings of your power supply and how important it is that all this stuff is designed so that so that you do get a nice clean DC power out, and then also that you're not trashing your AC power mains, okay? So I hope that was interesting to you, and seeing a close-up of those waveforms. I'm going to continue this. I'm going to take it up to full power. We're going to load this thing down, and we're going to watch what happens when it's loaded down, okay? And I think I will show you that inrush current on the transformer. I'm going to put the link down where I've done that before, okay? But I might have to save that for another video, because the second video, we'll see how far we get, because I did a lot of talking in this video just to kind of set up what we're doing and the reason whys and hows and all that kind of stuff. I hope it all made sense. Let me know what you guys think in the comments and what you think of those waveforms. And but what I want to do is show you the waveforms on the load, and I want to show you, are they clean? Are we seeing all this stuff getting reflected into the DC power that's powering our load? What's going on over there? So we're going to take a look at the power side of this when we bring it up. I started off small so you could see those those things that are happening. I think that is important to understand all that stuff. But now we'll bring up power, and then when we see the big peak currents and we have to adjust the waveform of the scope so that we can see the peaks of them, we're not going to see some of that stuff. But I will zoom back in and show you what's going on there too as well, okay? And we're going to pull out the picoscope to look at the secondary side. All right? Okay, guys, let me know what you think of this, and if it's helping you understand and see all the big stuff going on inside this thing, okay? Hey, thanks for watching, and 2 thumbs up to my patrons. Thanks, guys. Really appreciate you, and I really appreciate my members of my channel too. Thanks, guys. And my team member. Thank you. And let's say I don't know if we had anybody hit the super thank you button recently, so I might just show the last guy that did it. But all right, guys. Yeah, there is a super thank you button down below. One guy hit the PayPal thing. That was awesome. The Venmo thing. Those things are great because I don't take a big hit. I don't have to share it with YouTube or with, you know, Patreon. But I appreciate all the support, guys. And the iTech equipment, you know, they sent that to me for free. I'm going to do some more reviews of that stuff. But yeah, really awesome, right? Oh, MixSig. God, I think my current probes, my differential probes, I think everything I showed you today has been given to me by these guys between MixSig and iTech. So thank you to MixSig and thank you to iTech. So, whew. Okay, we're all set up. Let's do some more testing. Thanks for watching. We'll see you next time.